is one that Greg and I have given several times. We call it an intro to AI for national security, but more colloquially, we say AI 101. This is something as we've gone out and worked with DoD organizations to hold like design sessions and figure out how to apply AI to different mission needs. Find that it helps to level set and kind of bring everyone up to a baseline understanding of artificial intelligence. We'll usually start out these sessions. I'll kind of survey the crowd and say who here is really digging into AI, maybe fine tuning their own models or building their own GPT agents. And you get one or two people who will raise their hands and very confidently say, yeah, that's what I spend my nights and weekends doing. Then I'll ask who's at least played around with ChatGPT or Bard or some of these commercially available tools, and you'll get about half the room. And then who here, your extent of your AI knowledge is I can spell AI. And that is usually about half the room as well. People are eager to learn, but there's still a lot of people who just haven't had a chance to dive into the technology. And so that's what Greg and I are here to kind of level set and kind of get that baseline understanding. So if you're already a AI whiz, a lot of this may be redundant, but if you're new to AI, we're trying to give you that gentle introduction. I guess introduction. So introduce myself. So I'm Baron Stone. I'm our AI product lead with Defense Unicorns. And I brought along Greg, who's one of our elite AI software engineers to help me out here. So we'll be giving a brief history of AI, seeing how we got to where we're at today. Greg will talk a bit about some of just the technology behind modern generative AI. And then we'll look at how Defense Unicorns is bringing AI to national security missions and include some demos. So you can see this is not just things we're talking about. These are things that we're able to deliver today. So, if you read the news lately over the past year or so, or you can't scroll more than 2 minutes on LinkedIn without tripping over a half dozen articles and posts about AI. So there's a lot of action that's been happening over the past year and a half or so. And with all that buzz, it's easy to get kind of caught up in the hype and maybe a little dismissive about what AI can do. So I like to start a talk about AI just up front, because there's been so much hype about it, acknowledging that hype. So if you haven't seen one of these before, this is what's known as the Gartner's hype cycle. They do these type of charts for various technology fields. This one is for AI that they put together middle of last year. And basically the way this hype cycle works is for any new technology, there's some moment of innovation, and then everyone gets really excited and we ride the hype train up to the very top of expectations. And this thing is the greatest thing since sliced bread. It's going to solve all our problems. Then as people start to use the technology, they realize maybe it doesn't do everything the way they thought, or isn't all that was cracked up to be. And expectations fall down into the trough of disillusionment. And then over time, people understand the technology matures and we enter into the slope of enlightenment. And so I want to call out kind of two points here on this chart. And also note that AI is not just one thing. You'll see there's a lot of different flavors and subdomains of AI represented on here. So over on the far right, we have computer vision. So this is a very mature technology. It's been developing over the past couple of decades, really matured to the point of use every day. So if you whipped out your phone and snapped that QR code a couple minutes ago on the screen, you're using computer vision. You walk into a restaurant these days, they don't use paper menus anymore. You snap that QR code on the table. So it's something that's becoming part of our everyday life without even thinking about it. Maybe you've ridden around and used a Tesla's auto drive or advanced driving capabilities, computer vision. Also want to call out up at the tippy top of that hype curve is generative AI. And that's what our focus is going to be talking about here today. There's been a lot of really significant developments in generative AI over the past few years. So that's where there's a lot of hype around it. And so it can be easy to dismiss it because of all that hype, but it's important to understand that's just part of this natural flow. These technologies are evolving fast, crazy fast, actually. And so it's going to enter into that plateau of productivity. And so it's time to start investing in understanding these technologies and figuring out how to apply them to missions so that we're staying ahead of that curve as the technology evolves. So to just sort of, I guess, understand how we got to where we're at today, let's take a step back in time and just sort of do a brief history of AI. I say things, I'm on the internet, I'm doing this live. If I get anything wrong, please chat, call me out and keep me honest, but I'll do my best to accurately represent everything here. So let's go back to this gentleman, Alan Turing, who's often been referred to as the father of theoretical computer science. He was a British theoretical computer scientist. Now he's represented on the 50-pound note. So if you've been over to the UK recently, you may recognize him there. If you've seen him portrayed by Benedict Cumberbatch in The Imitation Game, great story. I highly recommend this movie. But he had a lot of significant contributions to theoretical computer science. Alan Turing, probably most famously known for his contributions during World War II to cracking the Germans' Enigma machine. So this Enigma machine was used to send encoded messages. They would send out radio transmissions to their boat subs and such with encryption. And that was how the Germans were transmitting their secret messages. The Allies could intercept those messages, but they couldn't decrypt them. And the Germans were changing the code on a daily basis, and humans trying to decrypt that within time was no use. So Alan Turing and his team of engineers built out this electromechanical computer called the bomb, which was able to decrypt those messages within a timely fashion that gave them actionable intelligence and that sort of decision advantage. And the Allies were able to use that information to save who knows how many lives. So that was kind of maybe what he's most famously known for, at least during the war. But that wasn't his first start in their foray into computing. Prior to the war, he came up with a concept in the 30s of what was known as the Turing machine. And this was a theoretical computer, not something that was physically realized, but it sort of, from a theoretical standpoint, defined what could and could not be handled by computer algorithms. And so this laid a significant foundation for that theoretical computer science field. And then after the war in the 50s, another thing he was well known for is what's in the field of artificial intelligence referred to as the Turing test, or he called it the imitation game. And this is a kind of theoretical mind test of how do you determine if a computer algorithm is, quote, intelligence. And so he came up with this concept of a test where you have a human player and they're interacting through some sort of a text-based interface. It could be like a chat bot on your computer. And the entity on the other side is either a human or an artificial intelligence or computer. And it's up to that player to determine, through questioning and interactions, am I talking to the human or am I talking to the AI? And if they can't tell the difference, then that would indicate the AI is sufficiently intelligent, being that it's able to imitate a human enough to confuse another human. So, Alan Turing kind of set a lot of this foundation for computing. But if you look at that bomb there in the middle, that's a giant electromechanical system. So there's only so much you can do with those big clunky computers. So there's a lot of other technology that needed to advance to bring us to where we're at today. So that starts with back in the 40s, the invention of the transistor. So this was able to take basically, instead of electromechanical relays, physical moving systems, and vacuum tubes, which are large and bulky, we could miniaturize down into solid state devices the ability to switch circuits on and off. And that builds a foundation for binary computing. Those transistors started as discrete individual components, but in the late 50s, they started to be able to develop integrated circuits where you're able to put multiple transistors onto a single substrate. And this allows us to build out computer chips like we know today. Sort of one of the really accelerating factors in the development of these computer chips was the Apollo mission. So when they were trying to build these rockets to go to the moon, they needed to build out these guidance computers and computational systems on board. Realized trying to build these computers from discrete transistors was impractical for size, weight, and power. And so integrated circuits at that point in time were still only a few years old, a very, very immature technology, but they realized that this was the path forward and led to the development of the first integrated circuit type computers, and that was to support the Apollo missions. Because of all that research and development into building computers, in the 70s, we started to see commercial processors available, starting with the 4004, then you got the 8080, 386 developing, and so on. And that led us into the 1980s, where personal computers started to get in the household, and you get great magazine spreads with Bill Gates seductively posing with his desktop. So you can see this sort of progression of from the original transistor all the way to computation, something that's getting in the hands of every person. And sort of during all this time, there's something famously known as Moore's law. This was Alan Moore at Intel made an observation that basically over time, the number of transistors in integrated circuits going to double about every 2 years. I think he refined that number maybe once or twice during his tenure, but that sort of became a self-fulfilling prophecy. It gave the semiconductor industry a target to aim for, but we really saw this rapid growth in the amount of computational power that computers had over the year. Yes, Andrew, I see that is crazy. And John Buchanan mentioned that the 386 had 85 stamped on it. Yeah, the 386 came, I think it was after the 70s. So we'll let that one slide, but good call out. Okay, so we have all this computational power, exploding power. What are we going to do with it? So the scientists at IBM in the 90s decided to see if they could build a computer that could beat a human player at chess, a grandmaster at chess. This was what was known as Deep Blue. You may have, if you're around back in the day, remember the news stories where they had developed this Deep Blue system and had played Garry Kasparov, who at the time was the reigning chess grandmaster. So they developed this algorithm in 1996, had a match between Kasparov and Deep Blue, and Kasparov was able to come across as the winner. Engineers went back to the drawing board and then had a second round with him in 1997. And that was when Deep Blue beat Kasparov. And so there's sensational in the news, computers are beating humans, be scared and all this kind of stuff. A lot of hyperbole there, again, a lot of hype around something new. But it did mark a significant point in the development of these computer algorithms and computing power to start to exceed human capability in very specific tasks, in this case, playing the game of chess. It's also worth noting that this was not artificial intelligence in the way that we think of it today. This was what we would call more like an expert algorithm. So IBM got a whole bunch of other really good chess players together, and they came up with algorithms and said, what is the best way to beat an expert, design those algorithms, and then just threw a whole lot of computing power behind it to sort of brute force their way across the finish line. So not AI, but it does mark a significant point in computing and towards replicating or exceeding human capability at tasks. Going forward, kind of into the early 2000s, something that you probably use every day when you boot up Netflix or YouTube or whatever. There was a lot of research going into recommender systems. Netflix actually back in 2006 put out a $1 million prize challenge to come up with a better recommendation system for suggesting people what they would want to watch. And it took a couple of years. I think it was in 2009 before that prize was finally claimed by a team of researchers. But again, it may not seem like a super complicated thing today, just like computer vision, because it's something we use all the time. But back in the mid 2000s, that was state of the art in terms of machine learning. In the late 2000s, going into the 2010s, there was also a big boom in computer vision. So ImageNet was a large database used for computer vision training, which was published in 2009. And then in kind of around the 2010-12 era, there's really a boom in these convolutional neural networks, basically using neural nets to do image recognition and image identification. And you can see now we benefit from all of that research with things like self-driving cars that are built kind of on that foundation of technology. And then one more kind of interesting milestone. So in 2016, sort of in the vein of the Garry Kasparov Deep Blue competition playing chess, researchers at Google's DeepMind decided to see if they could develop an algorithm that could beat an expert at Go. And Go being a game that is magnitudes of order more complex than chess. So where chess, you could brute force and represent all of the possible states of a chessboard throughout a game within reason. Go, there's too many combinations. It doesn't make sense to try and brute force an algorithm to beat a human player. So this is where they used a new concept, something known as an adversarial neural network, where rather than designing an expert algorithm like Deep Blue was designed to play chess, they taught this algorithm the rules of the game Go, and then just had it play millions and millions and millions of games against itself. And through all those games, it was able to learn and train itself to become an exceptionally good Go player. And then in 2016, sort of the milestone was they had it play the current world champion and beat him. So showed that these, this era of AI being able to learn and train and exceed human capability had come. So that is sort of in terms of artificial intelligence today, a huge step forward. And then Now we enter into the realm of generative AI, or at least generative AI as we know it. So in 2017, there was sort of a breakthrough with this concept of the transformer. And I know Greg's going to talk about it in a little bit. So Greg, I will not steal your thunder, but academically published in 2017. And that's sort of the basis for a lot of the generative AI models that we see today. So things like the large language models, the GPT models, and I've listed here kind of over the years, the evolution, specifically looking at like OpenAI's GPT models, but the number of parameters and just sort of getting across how these things have grown in scale and size drastically over the past few years, from the first GPT, which is just 100 million or so parameters, onto GPT-4 at, estimated to be 1.7 trillion parameters. So big growth. And there's also a lot of research going on now into how do we, not just balloon and grow these models larger, but also how do we more efficiently or, use smaller models to very effectively tackle specific tasks. And then also highlighting there's other modalities and new types of models and capabilities coming out every day. So if you played around with any of the image generation stuff, a couple of years ago, the results were a little bit creepy sometimes, or things are a bit off, but it's gotten significantly better very quickly just over the past few years, to where these things are in some cases producing things that are very hard to tell from reality, or realistic people. Security implications and things come along with all that. So with all these advances in AI, actually, Greg, have I missed any questions in the chat? I see the chat flowing by, but I'm having a
doing good.
All right, cool. So I guess, yeah, like taking a step back from that evolution of technology to where we're at today, on the world stage, leaders certainly recognizing the immense power and capabilities of AI. So from Russia to China to the US, we've seen a lot of big pronouncements from the leaders about investment in AI. Just last year, President Biden signed his executive order focused on how do we, deal with AI, safely and securely within the US. And we've seen Russia and China both investing heavily in building out their AI workforce and building AI tools and capabilities. So it's kind of this AI arms race that's spinning up. And the DoD also, of course, taking notice, and we're here, defense unicorns. We focus on the defense space. So, for example, just last year, the Pentagon stood up the Generative AI Task Force Lima to focus on, developing recommendations for how to best integrate and use artificial intelligence, specifically generative AI, for national security missions. And just like I mentioned at the beginning of this, if you're scrolling through LinkedIn or your favorite news feed, there's lots of news articles and things coming out of different ways the DoD has been trying to figure out how to bring AI to those missions to really deliver that decision advantage and keep us ahead of those other countries that are trying to get ahead of us. Whew. All right, I'm running out of wind, Greg. So I'm gonna turn it over to you to sort of demystify a lot of the technological stuff that can be a little intimidating when folks are reading about AI and hear these terms.
Sounds good to me. So in this next section, we'll break down sort of the fundamentals of generative AI and large language models, but we're going to try to keep it high level to leave some thunder for the remainder of the talks. So, let's get started with tokens. So a token should be thought of as a unit of information as the model sees the world. So we take in sequences of information, let's say in this case, a sentence. We break it into tokens, and each artifact in that sentence has a token, even the exclamation point, because that brings in new information to the sentence. And those go into vectors, which feed the large language model. And so ultimately we are the champions, contains 5 tokens in this particular case. Let's take a look at what happens next. So the as Baron alluded to in this paper called Attention is All You Need, we saw this widespread adoption of self-attention and the transformer model. And self-attention was a concept inspired by recurrent neural networks that basically allowed the algorithm to understand entities in a sentence as they pertain to other entities in the sentence. So if we just sort of look how the word making is positioned within this sentence, it has some relationship to other words in the sentence, like law, since 2009, the end of sentence token, and some of these other words like more difficult. And it has a strong correlation with more difficult, right? So making more difficult, puts together some information for the model. And this is brought into what's called a multi-head attention mechanism for the neural net. And that allows a feed-forward neural net to kind of decompose what is happening with the sentence in the grander scheme of this information. Again, trying to keep this slightly higher level because these concepts go deep, and there's been, thousands of papers now that have referenced transformers and introduced variations on this concept. But let's kind of take a look at what happens as we start to bring in more and more information into the transformer model. So essentially, actually, before we get to that, as we're feeding this information into the model, let's talk about the desired result, right? These models are predictive by nature, which allows them to generate things such as the next token in a sentence, hence generative AI. So in this sentence, the quick brown fox jumps, the LLM is contemplating what the next word is based on its relationship to the other words in the sentence, and it concludes with 70% probability in this example that over is the next word. And so that allows you to start generating sequences, because if you take that and feed it forward under the assumption that over was selected, now you can predict the or whatever the next word in the sentence is and do multi-token predictions. So we'll go to the next slide and kind of talk about this concept of a context window. This is probably one of the most important aspects as you're starting to stand up LLMs to understand, because as you inject more information into the model, it's trying to maintain context across all of that information. And with a 4K token context window or an 8K token context window, that's a relatively finite amount of information before things move out of the context and they're actually forgotten by the LLM. And so if you imagine you're sitting in a 2-hour meeting, you have trouble forming a relationship to the current sentences being spoken to the things that happened at the beginning of the 2-hour meeting. And the same is true of an LLM. And so these providers like ChatGPT try to drive up the size of this context window. So as you're having exchanges with it, that whole conversation fits into the window, and it can establish these ideas that they transcend just the sentence you're in, but across the whole conversation. So let's keep going. I'm not sure LLM. I might be saying LLM, which is large language model, which is what forms the basis of like ChatGPT or Bard. Let me know if that didn't answer the question. Cool. So let's actually talk about what a model is. Next. So a model is basically thousands or trillions in some cases, as Baron alluded to earlier, trained parameters. And these parameters, think of them as like coefficients in your most painful linear algebra class or algebra class ever, right? And so the computation itself is relatively simple, say ax plus b, but there's just trillions of those happening to form these relationships of knowledge. And the model itself is trained on things like Wikipedia or GitHub. And the large aspect of them is now that because there's so many trainable parameters, we're able to train them on just vast amounts of data. And that's been a major breakthrough, right? Because these large data sets that GitHub and Wikipedia have been able to curate by aggregating together knowledge on code and general information have led to these models that have very general behaviors, whether it be generating code or just generating knowledge or answers about knowledge in this case. And so through this supervised learning process, which takes on a variety of that supervised learning can be done in a variety of ways to create things like GPT or Llama or Falcon, right? We have these foundational models. And that forms the rest of this chain of reasoning that we're going to go through as we go forward. So the large language model, or the foundational model, really represents the language core of a larger system now.
How long does it take to train one of these models, or how much does it cost to build a foundation model?
Yeah, so this can vary dramatically, but I would say millions of dollars for something of the size of Llama. And it wouldn't be unreasonable for that to start to move into the billions in the near future, for models of that size.
So not a cheap endeavor, not a weekend hobby project.
Absolutely. And that's why you have companies like Mistral kind of focusing on making the smaller models, like the Mistral 7 billion model, that can be easily fine-tuned, which we'll talk about in the next slide, on things to help adapt it to other use cases.
Cool.
Two slides before we get to fine tuning. Cool. So I guess before we get to that, can a foundational model do it all? In a sense, no. In this particular example, we're asking it a series of questions that concludes with us trying to get to the nuclear launch codes. And while the model may try to produce an answer, the answer is probably going to be something like, I don't know that information, or even a hallucination, depending on how unconstrained the model is. But if it's not trained on the nuclear launch codes, it's not in that corpus of training data, it's not actually going to be able to produce a legitimate answer to it, because it can't guess information that doesn't exist. It just merely tries from things that it has been trained on. So because it's been trained on the capital of the United States, it'll probably reliably produce that answer. If it's been trained on auto manuals, it'll probably reliably tell you how to change the oil in your car. But nuclear launch codes, probably not, because hopefully those are not in a corpus of training data somewhere.
I hope that's not in the training. And just conceptually, the way I think about the foundation model is, it's like you've had somebody who's gone through college, got their 4-year degree and every possible degree that the university has. So they have a huge body of general knowledge. But there is, specific, domain specific areas that may still be unknown to them. And hopefully the nuclear launch codes are in that category.
Absolutely. So let's take a look at that in the context of a larger system. So starting from this college student that has a general body of knowledge, making it the language core, you might imagine, how do I get to a genius contracting officer, right? And that would start with some amount of that being contained within that foundational model, but it also needs additional context on things like the FAR or DFARS or other contracting examples. And so we can provide these additional domain-specific cases through new training data and fine-tune on that to make a much better model for that particular use case. Next slide. And so to take that to the next step, even if you want to get very precise answers and you want to guide the model, we have another concept, which is called retrieval augmented generation. And essentially, retrieval augmented generation is going against your knowledge database. Let's say you augment with something like some sources out of Wikipedia, or some documents like NIST or RMF. You would load those into your knowledge store and retrieve the relevant information from those and put that into the context window of the model that you're prompting. And so you can see, hey, I submit this query, I get back relevant information, and I'm appending that relevant information to the beginning of the query. So however many sequences of text that is extracted from, say, NIST RMF, and plus the prompt, which would be maybe a question on that. And then feed that to the model, get response, and that response would understand the context and be able to form complete sentences about that particular thing. Cool. So let's talk about how all of this comes together when we leverage the power of open source to deliver this AI for national security. So you might think like, hey, these large language models are expensive to make, right? But actually, despite that, there are thousands of these. And from those thousands, there are thousands of variations, leading us As of a couple days ago, when we took the screenshot, I believe Hugging Face, which is essentially the GitHub for models today, to 477,000 and change models. And so these models could be used in a variety of different ways, from extracting features from data to generating images to answering questions on documents, right? And so across all of these use cases, we have just lots and lots of different models.
And I see a question in the chat just popped up from Brad Sweeney. Do you see that, Greg?
Yep. Fine-tuning on-prem without compromising data to the cloud is critical in DoD applications. Sensitive domain-specific data can be used to fine-tune an LLM. Described. How do we solution this for DoD customers? We'll actually get to that. But essentially, the gist of it is keeping the data local to the user, which is called data sovereignty or data independence, and bringing the LLM to them. So we want to bring in these open source models, and we do that through this open source framework that we call Leapfrog AI. And so this is a suite of tools for configuring, deploying, running Gen AI in your national security environment, or anywhere you want to use this open source thing. And what is this actually? What's the unique aspect of this? That is, first, the data independence that I just alluded to, right? You retain control over your data. You don't feed it to an OpenAI or an Azure. You keep it in-house, and you bring this to you so that you can actually, do complex computation with your own data. We also focus on integrating specifically with your mission, because often you don't just want a general LLM. You actually want an LLM that is a capability that solves a problem for you, whether it's writing code if you're a software factory, or if it's helping you make decisions from data and getting the information you need from that data to make your decision. So we focus on that specific integration. And we also focus on the scaling of the mission environments. We've had everything from laptop on a submarine to a data center as potential use cases, right? And so we want to be able to scale to those various use cases. And stop me, Baron, if I'm missing anything in chat.
Yeah, no, I just saw John Oliver had a comment in there, sort of wondering if there's a way to reuse very expensive hardware stacks across multiple programs without leaking compartmented data. Because having everyone buy their own, especially these very large systems gets quite expensive. So that gets into that's even, I think, a bigger can of worms beyond just Leapfrog itself of data management and compartmenting out capabilities there. But kind of what you were just talking about, or with the ability to scale to different mission environments, if you're trying to bring AI to your organization and you don't yet have access to a giant enormous data center or whatever, Leapfrog can scale down to run locally on the hardware you do have available, so you can start testing it out, start working with it, evaluating it for your mission, and then as you validate that and want to adopt it and scale out, you look at what are the different targets and platforms to deploy to. But it is, and kind of what you're saying too on the data independence, it's Leapfrog is developed kind of air gap first or air gap forward. So always being able to deploy into environments where you could be connected to the internet. Sure, that's cool, but it doesn't expect that internet connection. So it works well in classified and disconnected environments.
Absolutely. Great. So let's take a look at the architecture of Leapfrog AI. And I think Baron made an important point when he was talking about this. This is designed to be an air gap first tool. So every one of these things should be able to run in some sort of environment at the scale we're talking about, without ever talking back to the internet, without passing your data outside of the confines of your boundaries. So inside of Leapfrog AI, color coding, acknowledge that we have a couple external apps that we integrate with. Let's start from the back end. So the back end you can think of as an engine that runs the large language model. So we take something from open source Hugging Face, we pull it in, and we power it with an engine like VLLM or Llama CPP Python. And this allows us to scale that thing to your hardware. So VLLM is designed to run on, say, GPU stacks. Llama CPP Python has a variety of things that it can run on, but everything down to a MacBook or a laptop, and that could be expanded to run on a GPU stack as well. So these are just the logics of how we power up the LLM, and then we expose that through a service endpoint. And that service endpoint you're going to interact with through an API. And so this API we wrote shadows closely the OpenAI API, allowing us to be compatible with a variety of different applications, including our own user interface. So these service endpoints will expose things like transcription or chat or embeddings, or even say image to text down the road, which is a work in progress. But that is in our roadmap at some point. And those go through our API server to an endpoint like the Leapfrog UI, which we'll show in a demo. So it's not just all, slides. But we can also integrate with something, say, like Mattermost or Continue Dev. I'll show a little bit of Continue Dev today, which is a plugin for VS Code for people that are, say, writing code. They're in an air gap. They don't have access to GitHub Copilot or some other code generation mechanism. You can actually just use Continue Dev with Leapfrog AI and get your code generation capability. And so there's other aspects to that, but those are the core things I want to cover. Some of these other aspects, like doing fine tuning, may be an external application where you pull in a model, you fine tune it, and then you bring it back into our backend, because we're focused on these runtime applications of these models and getting them into production environments in your air gap. So why don't we move along, Baron, unless you got anything to add to this?
Nope, I was just watching chat and I saw John Oliver from Mattermost is in there. So hey to our Mattermost friends, glad you guys are joining us here today. So yeah, if Greg, if you want to get your demos ready in the background, I'll talk to AI for national security. So Leapfrog is a set of tools. It's part of the solution, but it's not a full end-to-end mission capability. And so when we bring AI capabilities to national security missions as defense unicorns, we refer to it as artificial intelligence for national. That's a mouthful. I just AI for national security. Why did I try and read it while I'm looking at the slide? But this is sort of that full stack capability. So we deploy kind of going from the bottom of the stack up on top of our common declarative baseline, what we refer to as Unicorn Delivery Service. And this baseline provides all of those the things you gotta have for security and environmental control. So deploying into a Kubernetes environment, and this baseline provides things like your service mesh, your security monitoring, and so on. So out of the box, you're meeting a majority of the NIST technical controls, and that accelerates your time to getting an ATO, so you can actually use this system in production. Then on top of that, we're bringing in Leapfrog AI. So that was what Greg just talked about, our open source set of tools for hosting and managing these generative AI models in air-gapped or classified environments. Really, any environment you can deploy these to, commercial cloud type environments too, if you want to, but wherever you need to go. And then we work with understanding the mission needs to help identify what are the current state-of-the-art open source models out there, and what type of tuning or prompt engineering needs to be applied to those, and validate them for specific mission needs. On top of that, we have sort of an application layer. This enables connection to your mission data. So we can do things like Greg talked about retrieval augmented generation earlier, the ability to connect with current and dynamic changing mission data, so that when you're interacting with these models, they have that context, they understand what is relevant to provide you the generation results you need. And sort of some of the capabilities, looking at the little box over on the left, things that we have available today. We have chatbots, and that's what Greg will be able to show. So the ability to general Q&A type ask questions, as well as using it to assist in coding and development. So that's where the integration with continue.dev helps. We also have the capabilities to do transcription. So taking audio files or video files, if your organization has very long, lengthy meetings and you want to have those converted into a transcription, and if those meetings are classified, so you can't use the commercial tools out there, we have the capability to do that. And we can also then leverage these models to take those transcriptions and summarize them out. So if you need to take, you have all these meetings happening and you want to get a summary to sit out in your sit rep or, whatever reporting methods you have, this is a very good use case for AI. And in fact, Justin and John will talk in their next talk in about an hour or so about deploying that capability for use in classified environments for real world mission operations. And we also, with those models, we're using under the hood, if you're familiar with OpenAI's Whisper model, also has the ability to do translation in line with that transcription. So it can translate from a number of different languages into English. So if you're, have interactions with foreign partners and you need to transcribe meetings or whatever, we can also accommodate that. So that's kind of the snapshot today, January 23rd, 2024, of what AI for national security can do. But we have some other capabilities very near term on our roadmap. So what kind of referring to chat with your docs, that's the bringing that retrieval augmented generation in. We'll be releasing here very shortly in the coming months. We've got the underlying works built, and so kind of putting the finishing touches on that now, as well as looking at other capabilities. So doing structured document generation. If there's very specific reporting formats you need information synthesized into, being able to accommodate that, as well as incorporating more and more modalities. So doing things like image analysis, really kind of, I do that and more. There's whatever the mission needs. And so that's where we do want to talk to you. And again, I mentioned at the beginning of this session where, please, if you've got mission needs, sign up for one of these one-on-ones we're having tomorrow, or, schedule it with us whenever you're available, because we want to understand what are your needs so we can build the right solutions and make sure we're actually solving the right problems for you. And then, yeah, I guess, Greg, I'll turn it over to you to show this for real.
Wonderful. So I've queued up a few demos that we can do today, and I'll try to talk around some of the questions we have in chat around the differences between CPU and GPU performance. So GPU is always, well, for the foreseeable future, going to be preferred. But most of these demos I actually generated on my CPU because it's like a local development environment that I use from day to day. So this is our UI. It's much like many chat UIs, but it's open source, and it draws some inspiration from your typical chat interface where you have chats on the left and you've got some idea of personas on the right. These are just, if you take a look at a persona, it's basically just a configuration of a particular model with some system prompt, which gets embedded at the beginning of your prompt to tell the LLM how to behave, right? So think of these almost as like behaviors. So we've got one that's like a JSON coder one that we'll show today, and one that writes Python tests. We've got an AI academic that can answer questions about AI, a presentation assistant, which I've been experimenting with, still questionable, but it helps me maybe make content for slides, of which most of it wasn't used in this presentation, spoiler alert, because again, it still needs some work. But we've got a French translator, which works pretty great. You can just give it text and spit out French. And then ultimately a front engineer that helps me in my day-to-day, like let's say when I'm building this UI. You can also see that we've got transcription in here. So I've cached a transcription in a summary because that takes a little longer on CPU. So we'll take a look at some of those numbers too here in a second. But for starters, let's just say this is an LLM, right? I'm having, for those that are maybe a little new to LLMs and haven't used a ChatGPT or Bard or Bing, you can have a general conversation with it. I ask a question and I get a response. So I started out with like, what does the sun orbit? And ultimately it doesn't orbit anything, right? But through a series of prompts, I managed to kind of convince it that like, our solar system and galaxy are like orbiting around or rotating around the center of the universe or whatever. And we have an interesting philosophical exchange about that. Again, kind of interesting, not super interesting to national security yet. But let's say I'm in a SCIF and I'm building a Python application. The same model with slightly different parameters now can help me write a basic Python app with a SQLite database, right? And so if you're a developer and maybe you just get blank page syndrome and you want to get started, this will get you started, right? And I tried this out. It does compile in this particular example, and it does work. So this is just a way to get started with SQLite if you're developing an environment where you maybe don't have access to a Copilot or ChatGPT or Bing, right? And it runs pretty lightweight. This runs on CPU. This probably took 25 to 30 seconds to generate. Hence why I'm not doing these live, but we can see one live if anybody wants to see like what CPU performance is. But moving forward, I also did a little bit of SQL. So let's just say you're struggling with SQL queries and you just need to like select all the elephants in a database of zoos and maybe identify, zoos where exist both elephants and tigers, right? So just a general example, but it helped me write the SQL query for that. And so this is the power of this. This is all still the same Mistral 7 billion model under the hood, but just being prompted in different ways to give me different data. For those maybe that are a little newer to this, we'll keep going because there's some more interesting behaviors that we can talk about, right? So I made this JSON one, right? And this one can be prompted with a topic and it can respond in JSON. Which is useful if you're trying to maybe decide what your schema should look like, what fields do I need, and maybe what are some starting values for those. So I gave it, just for an example, something that would be within its knowledge base, the solar system. That's it. And it was prompted to spit back a JSON block about the solar system, and it gave me planets, right, and distances from the sun. The Earth is always 1 AU from the sun, right? Even though that doesn't necessarily, it's not the same kilometers or whatever from the sun all year round, but yeah, so it went through this, and actually you can iterate with it, right? So this is what's important. I was talking to Jared, who you'll see later today. He saw this response and he goes, well, actually there's 5 dwarf planets. And I said, well, I wonder if I told it, can you spit out all 5 dwarf planets, if I would get the right answer, because in theory it should know about all of them. And we'll just take a peek, and it got all the 5 dwarf planets. So I was able to kind of bring in my human knowledge and refine the results I was getting from the model by, letting it know what I wanted. So stop me if there's any questions in chat, Baron. Otherwise, I'm going to keep trucking because I can't see them.
I was gonna pause you there. So there was a question from Joseph Young. How many tokens per second are you getting on your CPU? He uses a 3090 Ti and gets up to 36 tokens per second. Do you have any benchmarks or rough benchmarks off the top of your head from what you've seen?
Yeah, so just take a look at my most recent backend run. So on my i13-900K, I'm getting about 26 milliseconds per token for that. And so we'll say across the runs, probably 20 to 30 tokens per second. I'd be surprised if on a 3090 you couldn't do a little better than that. So maybe one thing to check is whether or not the model is within the full is contained within your memory, or if it's moving information across the bus. Maybe try a smaller model like a Cynthia tuned Mistral or something.
So pick based on the kind of understanding those resource constraints, is that also impacts the models you want to use for given environments.
Yeah, one of the challenges is that when you load these models into memory, for like something like VRAM, right? If you run into the limits of how much can fit in VRAM, it starts using the system bus. And so now you're moving data across that bus at a much slower speed than what's in your VRAM. So you get better token generation rates if you can fit your whole model in that VRAM on your GPU. With the CPU, you're always using a system bus of some sort because it's just using RAM. But Max architecture is a little bit more unified with their ARM, so you might see better speeds on CPU on the Max than on your typical AMD 64 CPU.
Gotcha. And I'll highlight sort of, it was dropped in the chat there. I think Andrew dropped the link to our Discord for Leapfrog. And so, yeah, invite anyone, if you've got other questions or, after this, you're like, hey man, I want to talk with the Leapfrog community. Discord is sort of our main, I guess, the main town hall or environment for the Leapfrog team. So, the conversation doesn't end when the live stream ends.
Definitely. Yeah, so would love to engage more on, the different specifications of your system. So jump into our Discord. Maybe it also can come down to like which backend you're using. If you're using something like VLLM that's specifically tuned for a like a GPU type system with NVIDIA GPUs, or using something more general like a C transformers or C translate type backend. So all lots of variables that can affect your token generation rate there.
Yep. We got a request here from Rob, who's our boss, and he was asking, can you show a non-pre-generated example so we can see
Abs-
things running?
Absolutely. Well, so let's just say um, we'll go with JSON coder. And we will say Animal Kingdom, I guess. This might produce some interesting results. So this is running live. According to my Docker on the side, getting on the order of 27 milliseconds per token for eval time. So it'll go a little slow, and at the end we can convert this to a code block to see kind of how this will look in a JSON form. So we'll just kind of let this run for a second. If it goes on for more than 20 or 30 seconds, we'll kind of talk about some other things.
In which, I looked down for 2 seconds. Which persona were you using for this one?
So in this one, we're using the JSON coder persona, which basically takes any topic and it spits out a JSON block based on that topic. And these are a lot of words that I'm really unfamiliar with, so I wish I would have picked a different topic because I don't know my biology quite this well.
It looks like a lot of Latin words to me. I'll assume it's correct.
Yeah, maybe I should have picked just something that's code because I know code very well.
While that's going, I saw one other question from Riley Kiefer asking about, so yeah, we had image analysis on the roadmap. That's a little bit farther out, and it's what the specific details of how that plays out, that again goes back to understanding what are the mission needs, and so what features we need to incorporate, and looking at what is currently in the space of open source models that we can pull in to apply to that problem. So don't have a full feature list to share at this time, but if you've got specific needs, please, yeah, that's where we'd love to talk with you offline to understand that and make sure we're building the right capability.
And to give you an example, what this looks like in the back end, I suppose I could share my Docker, but it's also interesting to watch it converted to code block. We're using about 3.6 gigabytes of system memory for this size model, and we're running on about 15 threads. So it's got a fair amount of CPU horsepower behind it to get this token generation rate, but this could realistically run on a laptop, preferably not on battery though. Like I would want the laptop to be plugged into a power source and running without the battery reductions in computational power. Cool. So I also cached a transcription in summary, but this one will actually show the times of execution. Yeah, Apple Silicon is very good. I even have an M1 Mac that runs great. The new M2s and M3s are so fast. But so on the side, I kind of wanted to talk a little bit about transcription and summary, right? Like this is the value that we're trying to approach with something like Leapfrog AI and AI for national security, is that you can bring in a variety of backends, and if you keep them a small form factor and you scale to the target environment, eventually you get interesting behaviors by bringing them together, right? So I ran in this case, I just took an extract from Uganda folklore. Thank you, Gato, one of my teammates, for just providing me a 5-minute clip of sound that runs pretty quick. This ran in about 30 seconds. Sorry, a third of a minute, which is maybe 20 seconds, 20 something seconds. And it just produced a transcription of this. And so it's just a wall of text, right? Not super great. But imagine that I feed this back to my language core that we talked about earlier. We ask for a summary, right? Cache this one because this one takes a full minute to run. We could see it go live if you wanted to, but it's just going to spit this out in one wall of text after a minute is what you're missing. So this actually gives me kind of a bottom line up front or an executive summary of the clip. It's funny because I'm actually using the templating prompt that we use for like summarizing meeting notes and stuff like that. You could use a different templating prompt to get more of like a distillation of the story, like give me a Cliff Notes template or something more like that. But in this case, I'm using my meeting templating, and it's just giving me the bluff. It's giving me about 5 bullet points, and it's saying there are no action items present in this audio clip about Uganda folklore. So this is where you start to get these multi-agent behaviors that are interesting, right?
I'm glad there's no action items out of a folklore tale. That'd be no fun.
Yeah, it sounds more like a homework assignment.
Yeah.
And I also promised if we've got just enough time for one more demonstration, that I would show us integrating with an external tool. I picked Continue Dev for today because I didn't know we were going to have a ringer for Mattermost, or else I would have picked Mattermost. But we'll just take a look at my my VS Code instance, which I hope that's what's sharing now. And we're using Continue Dev, which is an air gappable extension that does it interacts with your code, right? And so this line that I supplied to it basically inspects my Docker file that is contained within this project. So we can see it's right here. So I'm in our Leapfrog UI, and Docker files here on the right. It's open source. I'm not sharing any, trade secrets. We open source a lot of, if not all of our software. So you can come down and inspect it. And really, I want to understand how this is working. And, at first glance, it's a lot of text to read. But if you're, say, an airman in a skiff, you have some code, you're maybe making some scripts, helper scripts in Python to help with the mission, right? But you don't necessarily understand how some of this code that's been written by the airmen that came before you work. This allows you to inspect it. I can also, inject some errors into it and refactor this live, but it's a little bit slower, and we're coming up on the end of time. But I encourage you to get it, say, Continue Dev into your IDE and start experimenting with it, because it's super powerful and it integrates with an OpenAI API. So in our case, we're just using Leapfrog AI.
Is that the
That's the end. I'm feeling bad about not pulling up Mattermost, but I don't know if I can do it super fast.
Yeah, maybe when Jared for his session, if we'll see if we can work that in there for the third session today. But we promise Mattermost integration is a thing. It works great.
Yeah, we're teasing you so that you come to Jared's session at the end of the day, even though you're going to be tired. He has it actually just running on his system that we use very regularly for demos. So,
yep.
Also air gappable.
So let me share my screen here. Get the final slide back up. So I guess, yeah, pause here, see if there are any last minute questions. Let's see, I saw Chris T had a question. How long would it take to demo the download configuration installation to the point of this prepared demo of the running Leapfrog answering those queries? So I guess going from nothing to getting everything installed and up and running.
Yeah, so we have a few different installation paradigms. If you're dealing with a production data center application of Leapfrog AI, it's certainly not going to be the same velocity that you could get today's demo running. If you use something like Tadpole is designed to get Leapfrog AI up and running in like 10 minutes or less to this point of demo ability. But that's what we use to expediently stand up demos and maybe do some dev locally. If you want to go to prod, we've definitely installed production Leapfrog AI in under a day. Within a few hours, being able to have things running in production.
Yeah, and that's where, if we're going into production, sort of that what you saw for the AI for national security, that full stack with on that UDS core baseline, there's a lot more that, yeah, in a production environment we bring along with us. But Tadpole is another route for if you just want to get your hands dirty with looking at the libraries and stuff. For dev stuff, that's another route we can deploy. Let me see.
And I saw Joseph Young's just talking about requiring OpenAI. So you don't have to send anything to OpenAI. With Continue Dev, you can write a configuration for your backend that would use Leapfrog AI, and our API shadows the OpenAI API. So you would just be using us. Nothing would ever go to their servers, and in an air gap, that is a perfectly tenable situation. So definitely be excited to hear if you try that out.
Yep. I saw another question. I'm making sure I didn't miss any questions here. There's another question on the timeline for adding RAG. So that is something we're actively working on right now. Right now we're doing this this session, but this week we're working on, and so aiming to have that out no later than the end of the quarter. So that's our next near-term capability. So being able to enable what we call chat with your docs, so you can through that Q&A, have that context-aware generated response, pulling from your mission-specific data in your environment. I think that was all of the questions. I do want to remind folks. Oh, I just saw another question pop up. Christopher Keith, do you have guardrails or prompt tuning capabilities as part of this stack? Greg, do you want to take that one?
Yeah. So we today don't use guardrails. We mostly focus on use cases where the customer is aware that the LLM could hallucinate, but we prioritize around the types of questions and prompts that they're going to be asking. But we do want to add guardrails as an option and give, say, power users the ability to adjust those accordingly so they get the best behavior out of their models. So anything from whitelisting certain prompts, so that way you don't have people just asking it anything, to ultimately, checking the outputs that are coming back to make sure it's within certain parameters. That's kind of what guardrails are for anybody who's unaware. And that is absolutely something we want to support in the future. But again, today we don't use those. We use system prompt tuning, which just gives the behaviors that we're looking for in the models. But they could break outside of those behaviors, especially if you have a user that is comfortable with LLMs and knows how to find the edge cases.
And I think Christopher also had a follow-up comment there. And so it may have been when he was referring to guardrails, it was more like access controls and data permissions on who can access what data. Because he said many of his customers want to filter or restrict access of their data to certain groups, like what can the contractors see, what can the government people see, and so on.
So in a RAG setup, that's extremely easy to do by just determining, what goes into your database of RAG queries, right? So the LLM is not going to come pre-canned with necessarily knowledge on your data. And if you just ingest the data into your companion database, say a Weaviate or a Chroma, that is relevant to that group, and make sure that when it's queried, it only returns, say for contractor or gov, you're going to have a much